Okay, thank you very much for the introduction. It's very polite of Dimitri to say it's a talk of general interest. Systematic errors are not anybody's favorite topic. It's not nearly as interesting as the theory, the detector, the data processing, the fun things you can do with artificial intelligence and neural networks, boosted decision trees, and so forth. Nevertheless, I expect that most of you have got a thesis or an analysis note or a draft paper or something containing several chapters, sections, the detector, the theory, which you're having fun writing. And one of them is entitled Systematic Errors. And you're thinking, what am I supposed to do with this? Everybody's got one. You have to do it, but I don't really want to. Where do I start? So what I'm trying to do, I hope today, is not give you a bunch of formulae and programs, but to show you a way of thinking about what systematic errors are, and more importantly, what they aren't, because there is a lot of very bad information and bad practice out there. Less, I'm happy to say, than there was. I think from BaBar onwards, some of us have managed to convert people from the ways of error. But if you go to your supervisor or your supervisor's supervisor, they will tell you things which are in contradiction to what I'm going to tell you. So be prepared for a bit of conflict. In the days when your supervisor or your supervisor's supervisor learnt their trade, then you were lucky if you got a couple of hundred events, which meant that your statistical errors were of the order of 10%, and they were huge compared to the systematics. So the fact you were getting your systematics wrong was not too bad a problem. These days, we have particle factories, we have easily got millions of events in our data sample. We talk about precisions of which are parts per mil, and it really matters that we get our systematics right. And what I'm saying is that there has been a general tendency to overestimate them. They are overestimated because people are ignorant. Ignorance leads to fear. Fear leads to suffering. Suffering leads to pain, and pain leads to the dark side. We know that. So people follow the familiar rituals that they hope will keep them safe without fully understanding what they do. So I want to start by talking about what a systematic error is and what it isn't. Then I'll talk about how you handle them and how you find them. That may seem the wrong way around logically, but it makes sense when we get to it. Then I'll talk about the need to check your analysis, which fits into the systematic framework. So, what is a systematic error? Rhetorical question. Here are two answers. One is given by Bevington. Bevington wrote a brilliant book called, if I remember, Data Reduction and Error Analysis for the Physical Sciences, 1970s or so. It was one of the first books on proper computing for physicists in the days when Fortran was a new language. And in many ways, it's brilliant, but he has a view on systematic errors. Then there are ORIA's notes on statistics for physicists. ORIA's notes, again, are photocopied, scanned. Pick them up when you can find them, and Google will find them for you. They are good in their own right, and they are the notes that J. ORIA took in his statistics lectures, and his statistics lecturer was Fermi. So they're going back to him. Bevington defines a systematic error as a reproducible inaccuracy introduced by faulty equipment, calibration, or technique. And we could read that and think, yeah, fine, I understand that. ORIA defines systematic effects is correct grammatically, though you do have to think about it. Systematic effects is a general category which includes effects such as background, scanning efficiency, blah, blah, blah. We would probably want to update that these days. The uncertainty in the estimation of such an effect is called systematic error. And we would read that and think, yeah, fine, I understand that. I've got my head around that. However, these are contradictory. They are saying different things. They are different definitions. That's obvious. I am going to assert that ORIA and Fermi's definition is right, and that Bevington's definition is wrong and unhelpful and misleading. And it's not just Bevington. You will find this or words like it in a whole lot of other books and websites or what have you. So if you go off and you find that Wikipedia says so-and-so, just because it's on the web doesn't mean it's true. It goes back to basic undergraduate teaching, as we tell our students in the laboratories. There is difference between measurement errors and mistakes. To put a simple, rather over-obvious example, if you've got a voltage which is actually 12.3 volts, but your voltmeter is actually only accurate to put a tenth of a volt, then if you measure 12.4 or 12.2, then that's fine, that will happen. Even if you measure 12.5 or 12.1, provided you don't do it too often. That's a measurement error, and it's all part of the game. If you miss out the decimal point and write down 124, then that is not an error, that is a mistake. And what Bevington is doing is he's describing systematic mistakes. Going back, he's talking about faulty equipment, calibration or technique. He's talking about mistakes. ORIA is describing uncertainties, which are errors in the way which we define the term in physics. So when talking about systematic errors, you have really to know which you're using. Are you talking about an uncertainty or a mistake? Hopefully, you're talking about an uncertainty. There is a school which says you should never talk about systematic errors. You should always talk about uncertainties or mistakes as appropriate. But that's hard to avoid. I couldn't even avoid it in the title of this talk. But you should always know which you mean. So when you're talking about the spurious discovery of a faster than light neutrino, that was not caused by a systematic error. That was caused by a systematic mistake. An optical cable was not plugged in properly. So know which you mean. So examples of systematic errors, which really are errors, which are uncertainties, some standard ones. Suppose you're measuring the momentum, the transverse momentum of a track in your detector. Then the momentum is given by 0.3 b rho, units being G V over C, Tesla and meters. And you've measured the radius of curvature rho from a set of points along the track. And so it has a statistical error on it, which is different from one track to the other. But there's also an error on the magnetic field. You don't know that absolutely precisely. There's an error on that, which will apply to all tracks. All right, probably that's a simplistic view. What you have is a complicated field map, and you do Kalman fits through it and so forth. But the principle is the same. There are statistical errors on the measurements from track to track, and there's a systematic error on the magnetic field. Going out from the tracking chamber, you get to a calorimeter, presumably, where you have energy from photons in photomultiplier tubes or photodiodes or whatever you use. Call this signal D. Then in each crystal module, whatever it is, you've got an energy which is perhaps, if you're lucky, a linear function of the signal. Perhaps it's more complicated than that. Again, you have statistical errors on the light signal caused by whatever these particular photons do and Poisson statistics in this particular particle. And you have systematic errors from the calibration constants, which you've evaluated in a test beam from Monte Carlo or what have you. More pleasantly, you can just use algebra when you're trying to find out a branching ratio. you count the number of events in your channel, fine, ND. That's got a statistical error, which is Poisson of the square root. You subtract the estimated background. You divide to give you the actual number of events you've got there. You divide by the efficiency to give you the number of events you would have had if you had perfect efficiency. And then you divide by the total number of events to give you a branching ratio. And all these three, the efficiency, the background, total number of events, have got uncertainties on them. The total number might be statistical, but it's more likely to be uncertain, not likely to be systematic because it comes from a luminosity and what have you. The phrase nuisance parameter is a very good one and helpful one. It's a nice way to think about them. You have parameters like the branching ratio that you're interested in and are unknown, and you have parameters like the background, which are not exactly known, they have uncertainties in, and you're not interested in them. So using that, I should pause to acknowledge, are they Bayesian or frequentist? They can be either. I don't want to go into the great Bayesian versus frequentist controversy, if there is such a controversy. I will just say that there is a frequentist view of statistics, there is a Bayesian view of statistics, and both of them have advantages and weaknesses. As a physicist, you have to be prepared to use both. Both have something to say, and you do always have to be clear about which it is you are using and not get them confused. So when you've got something like the magnetic field that was perhaps measured by an NMR probe or something, that's a perfectly honest to God frequentist experiment, sometimes called the ancillary experiment. Calorimeter calibration, again, perhaps that was done in a test beam, that's the ancillary experiment. The Monte Carlo simulations can also be of this type. And sometimes the ancillary experiment is actually the same as the main experiment. For example, when you're calculating backgrounds from side bands in a similar channel, or possibly even the same channel in the actual data, but that's not a real problem. So these systematic uncertainties can come from honest to God, no nonsense frequentist experiments. There are also instances where they're clearly Bayesian. You've got a formula that predicts the cross section, which you need. You ask the theorist how accurate it is. You probably have to explain to them quite carefully what it is you mean, because their first response is, it's completely accurate, I calculated it properly. But then you have to explore things like, well, you only calculated the third order, suppose you could have calculated the fourth order, how much of a difference might there have been, that sort of thing. But they may say, all right, well, it's good to 5% or 1% or whatever. And that's clearly a Bayesian, it's a degree of belief probability. It's not just theorists. Your experiment expert may tell you that the calibration of your drift chamber, it will shift during the run, yeah, but not by more than so much or so much. You keep track on it as best you can, and it won't vary too much. And that, again, is some Bayesian idea. So you have to be able to use both, and some analysis techniques use a hybrid of the frequentist and the Bayesian, and that's fine, again, provided you know what you're doing. You handle these using correlations. And this is actually straightforward. They obey the standard combination of errors formula, except you have to use a slightly more complicated form. It is traditional. You have no doubt done it many times. You give a result as the value, the central value, and then the statistical error, and then the systematic error. We do that because we do that mostly. You will find some books which say you can't combine the systematic and the statistical, but this is rubbish. You can. If we wanted to, it would be perfectly valid to write that as 12.2 plus or minus 0.5, 0.3 squared plus 0.4 squared, meaning being 0.5 squared. But we prefer to write it as 0.3 plus 0.4. There is a small piece of useful information that gives us straight away. if you could take much more data, yep, then you could reduce that 0.3, and you could get the total error down, but you could only get it down as far as 0.4. So by giving the relative sizes of the statistical and systematic errors is a quick way of saying how much more you can expect the result to improve when you have future years' data, assuming that the systematics stay the same. So for a single estimate, single measurement, it's really just a convention. Where you've got several measurements which are correlated, for example, you've got a whole set of branching ratios which have a common luminosity error or efficiency or something, then the results are correlated, and that correlation is important. And there are people in groups like the particle data group and the heavy flavor averaging group who spend their professional lives looking at this 0.4 and other people's numbers and working out which of these errors are shared between experiments, between results, and which of them are separate. When you've got that structure worked out, you do it quite straightforwardly by writing down what's sometimes called the covariance matrix, or sometimes the variance matrix, sometimes V and sometimes C, doesn't matter. It's the generalization of the variance, the standard deviation squared, which has got the usual errors along the diagonal and the systematic errors off the diagonal. And you can construct that if you've got several experiments with shared systematics between some of them. You can have a complicated block matrix structure, and you can then use that in chi-squared, maximum likelihood, what have you, just by taking the, rather than the 1 over sigma squared in the usual mean squares, you sandwich the inverse of the variance matrix between the prediction and the measured values as vectors. You can see that that's the same if it's a diagonal, and it works out to be the same if it's got covariance of diagonal terms as well. This works simply for additive errors. It also works a bit of a fuss for multiplicative errors, which are perhaps rather more common. Faced with this sort of combination of results from different experiments, and it's not just people like PDG that have to do this, you might have to do this if you want to combine the results you've got this year with the results you had last year, or the results from the muon channel with the results from the electron channel or something. It can work within experiments as well as between them. One way of doing this is to write down this matrix, which is big, invert it, and find the minimum chi-squared. Another way is to use just the diagonal terms, but to introduce a separate offset, saying, I think there is a, there is an additive bit which I first guess is 0, but it has a spread of S or something, and introduce that so you have a simpler thing to minimize, but more variables. And it turns out that these two apparently different approaches turn out to give exactly the same answer and exactly the same errors. And there's a reference there if you're going that way. So that's all assuming that our errors are nice and Gaussian, which they often are. If they're not, as sometimes happens, then you're reduced to looking at likelihood plots, like perhaps the one on the left. Here, supposedly, we have a horizontal axis A1, which is what I'm interested in, and a vertical axis, which is A2, which is a nuisance parameter. It's an efficiency or a branching fraction of something else or something which I don't care about. And you're interested in the one but not the other. And you've got a double likelihood like that. And what you do then as a frequentist is something called the profile likelihood. That is, you scan across the value of the parameter you're interested in. And for each of them, you find the maximum likelihood, that is the value of the nuisance parameter that gives you the maximum likelihood, and then sketches out a path like this. It's like a path across a hilltop that goes along the top of the ridge. And then from this likelihood, you read off the maximum and the delta log L equals minus a half on either side. This is converting it from two parameters to a single parameter. There is a sort of justification I can offer you for this. It's not much, but it's the best you're going to get. Suppose it happened that our likelihood didn't look like a sort of squelch like this. Suppose it looked nice and factorized like this. I think I've drawn it as Gaussian. It doesn't have to be Gaussian. Perhaps that's misleading. The point is that this likelihood or log likelihood as a function of A1 and A2 has been reparameterized, so it's a product of the two individual likelihoods. Now, if you take any value of this A2, which has been transformed, if you step across, you get a shape in the likelihood function, and that shape in the likelihood function as a function of A1, the interesting variable, is always the same. It's shifted up and down, but that doesn't matter because we're dealing with maxima and delta log L equals minus a half. So whatever value we choose for A2 prime, we have the same likelihood as a function of A1. So we can say the maximum is the delta log L equals minus a half, values are so much, and we can read off the value and the errors on A1 here. Now, if we don't have that, perhaps we could transform it from this shape into that shape by a just sort of distorting, pulling the elastic sheet around on A2. Clearly, in this case, you can. Clearly, there'll be lots of cases you can. Clearly, there'll be some cases where you can't. If you've got something which has more than one bump in, then you can't transform it to something like this. But let's suppose, for the sake of the argument, that you can. Then you could transform this to here. You can make a statement which is true for any value of A2 prime. And if it's true for any value of A2 prime, it's true in general. So you just have to take any of these lines and you get a result which is true in general. But you don't even have to dig out this transformation and work out what it is, because this curved line here, which is the peak at each point for at each value of A1, maps directly onto this straight line here. It's the one line which is preserved and identifiable and preserved. So by tracing out this profile likelihood, you're tracing out this likelihood, which is the same as any other likelihood. So you have a general result. So profiling is one way to get rid of a nuisance parameter. Another way is to marginalize. Marginalizing is just a sort of technical statistical term meaning integration. So rather than profiling this thing, you just integrate over all possible values of A2, which looks an obvious thing to do, but it is strictly Bayesian. If you're a frequentist, you are not allowed to integrate likelihoods over parameters, because if you were to reparameterize in terms of root A or A prime or square or A squared or sine A or something, you would get a different result. Another way of saying that is if you had a different prior for A2, not flat, but something else, you will get a different result for your, I think, peak and certainly limits with A1. So you can do it, but be careful. And really, if you do it, you should try various different priors for your nuisance parameter A2. So that's what you do with them. Now let's go back to how you find them. And there are, I think, useful to divide them into three types. The good, the bad, and the ugly. The good is what we've basically talked about so far. You've got some explicit continuous parameter, which, okay, it's uncertain, and you can feed it into the algebra, and it all just follows through either with a simple combination of errors formula or with lots of correlations, but the matrices will handle that. Somewhat more complicated is suppose you've got a continuous parameter, but which doesn't just feed into the algebra. For example, you've probably got a Monte Carlo, Pythia or Fritjof or something, all sorts of them, which contain tuning parameters which are known to some extent, but not completely. For example, the spread in transverse momentum in a jet is something usually which you allow to tweak, or lambda QCD or what have you. And actually, there are probably many of these, and tweak them in a compatible way, but that's another story. So suppose you've got this parameter, this nuisance parameter. This is your results on the vertical axis, and you can change your parameter up by 1 sigma and down by 1 sigma, and it will go up by 1 sigma in R and down by 1 sigma, or possibly down by 1 sigma in R and up by 1 sigma in R, same difference. So you just change it by sigma and you read off the change in sigma. If you are lucky, then, as drawn here, if you go up by 1 sigma, it changes by the same amount as if you go down by 1 sigma. If it doesn't, then you could introduce asymmetric errors, but that is a whole other can of worms, and my honest opinion is that you should avoid that if you possibly can. So if you have, say, plus 0.5 and minus 0.3 for your shifts on the result when you shift the parameter, then I would write that as plus or minus 0.4 if I possibly could. Yep. If it was plus 0.6 and minus 0.2, I probably wouldn't be wouldn't be sort of prepared to reconcile it with my conscience. But if you can, then you should. Asymmetric errors are to be avoided if you can. Second point to say about this, I've drawn it, as you can see, with a little error on this point and big errors on these points, which I think is representing real life. These errors come largely from the Monte Carlo statistics. You have lots of Monte Carlo statistics here, because this is the main analysis where which is going to matter, whereas these are subsidiary Monte Carlos just done for some sort of systematic error estimation. Unless you've got a very generous computing system, you're unlikely to get so much data for that, so these errors are probably bigger. Okay, looking at points like that, you're tempted to say, well, I could draw a straight line like that, but I could draw a steeper one or a shallower one quite easily. Shouldn't I fold that uncertainty into my estimate and increase it? And some people do that. Technically, this is wrong, because if you do have a tendency, your uncertainty on points, then that is always going to tend to increase the slope. You can prove that by writing it out, the expectation values explicitly, or you can see it quite easily. Suppose you had a variation which was in fact, in truth, absolutely flat, yep, but you're measuring this with some sort of precision, then that's going to push it to have a gradient one way or the other and give you an apparent uncertainty which is not in fact there. So technically, the correct thing to do is to subtract these uncertainties in quadrature. However, you will never get that past your review committee, and I don't advise you to try it. I just advise you to ignore it. If there really is a big effect, then you've got to go back to your computer allocation people and grovel to them and say, look, I really do need more data on this. Another way, which only occurred to me recently, when I met people doing it, if you've got lots of computing around, you don't have to just take plus sigma and minus sigma. You could also take plus 2 sigma and minus 2 sigma, or you could just take lots of different values of this parameter distributed in a Gaussian way and read off the distribution in the results. And avoids all this uncertainty, this statistical uncertainty, asymmetries, and all that. So that is continuous parameters where you understand what the parameter is doing, but you don't have a direct algebraic line to the answer. The third and worst class is where you have many models, discrete uncertainties. Models are a typical choice of that. Suppose you've calculated your background using JL4, fine, and somebody says, well, you know, JL4 is fine, but you can't, it's not the gospel. So you think, all right, I'll also calculate it using Fluker, and you get a different result. Well, you're not going to get exactly the same result, it's going to be a bit different. So you've got two results, call them R1 and R2. If your first result, R1, is one you know, it's the standard, it's what you're working with, and R2 is just brought in as a typical other view, then you can stick with your value and give it an uncertainty, which is the modulus of the difference. Why that? Because that is the only number you've got. If you want to multiply that by root 2 or root pi or divide it, I'm not going to say that's wrong. It's just this is the only number you've got, is that difference. And it may be that you happen to be lucky and get two very close numbers which aren't really merited. That's just part of the game. It's all you can do. If you've got two models, you're not going to say that one is the canonical one and the other's just an outsider. You're going to give them equal status. Then you take the mean of the two, and you might divide that difference by root 2. But if you didn't, I wouldn't shoot you for it. If you've got many models, you can take the root mean square difference with Bessel's correction, or some similar mean value. If you've got two models which are extreme in the sense that, not that they give extreme different values, but the physics that goes into them is extreme, then you can take half the range, and for an error, you can take the difference divided by the square root of 12. Suppose you've got some state which could be produced, some meson which could be produced in a polarized state. And it might be produced in a completely unpolarized state, or it might be complete 100% polarized. You don't know. So you could take unpolarized and fully polarized, and it's got to be somewhere between the two, and you don't know where. That gives you, the point is that root 12 here is a nice big number for pushing errors down by. It is Bayesian. It comes from saying the truth is somewhere between model 1 and model 2, and I have absolutely no prejudice and idea as to where it is in there, so I'm going to assume a uniform prior. It's a bit iffy, but that is what you do. And for all of these are just ballpark estimates. Don't go to the wall for them. If the difference you've got is not small, then you've got a problem. But actually, you can turn this round. If you've got two models which give very different results, then perhaps you can use your result to tell the difference between those two models and change the question that you're asking of the data. So here's an example of that. Suppose you've got a nice signal there, and there's a background. This could be sort of some mass of some combination. You count the number in a region where the signal lies. You have a region, two regions, keep it fair, out here where there is background, and there's regions in here we're not going to look at where there's a bit of both. You fit, say, a quadratic, that's this red line, to the background in the two cases, and you use that to subtract off from the number of events in the signal. So you've got a raw data number, count the background, estimated from side bands. Fine. You have no great reason, or probably you have no great reason to believe it's quadratic. You just try it and it works. So you could try lots of other things as well. And you get these other curves in here, and you'll see you get very different not very different, slightly different numbers of signal events, it will change. So in this case, we just used a quadratic because it fits. It's not a phase space model or something which would have some sort of cloud to go with it. I suppose that all the functions we tried do in fact give acceptable fits to the data in the background region. Otherwise, you can throw them out, fine. If you know the likelihood function completely, including the peak, then you can actually do something clever outlined by Paul Dauncey and his colleagues, called the profile envelope method, where you kind of assume that the choice of model is a Newton's parameter in itself, and you get a whole lot of chi-squared-like envelopes and can map out the profile outside of those. So that's something to look at, but you do need the whole likelihood function to do it. That includes describing what goes in the peak. And so far, we've just been doing a raw count. So I've said for the uncertainty, you take central analysis, you can stick with the quadratic, or you can take the average, and depending on how you feel about it, what sort of status you accord to your models. For the uncertainty, you can take the root mean squared deviation or the mean absolute deviation if you like. Neither of those is obviously wrong. What is obviously wrong, and what some people do, is to look at these various models and say which of these has the largest deviation from the red line, I think it's the black line, and take that as their systematic error. That is wrong. It's wrong because it is over-conservative. It will inflate your errors. You can't really represent a set of values by taking the maximum. And it's obviously wrong because it penalizes diligence. The more functions you find, you try, then the more likely you are to have one which is some way away from the average or the typical value. So do not, when you're faced with a set of possible numbers from different models, do not say we take the maximum value and that we will use as its conservative. When is it correct to take the maximum deviation? In two cases, which probably don't apply. If you are an engineer, and I've got nothing against engineers, then when you quote a plus or minus, you're quoting tolerances. If you've got a 99 plus or minus 1 millimeter peg, and you've got a 100 millimeter hole, then you want that peg to fit into that hole every time, not 68% of the time. So if you're an engineer, you should be quoting tolerances, but if you're a physicist, you should be quoting standard deviations or 68% confidence regions. There is a construction, it's a bit obscure, so I'll take you all the way through it. What do we mean by the error when we've got a non-Gaussian distribution? There are two possible answers to that, both of which are plausible, and I don't want to go into which is which. You can define it as the RMS spread, or you can define it as the 68% central confidence region. Of course, if you've got a Gaussian, they're the same thing. For systematics, if you're talking about a final result, there is a case for talking about the 68% central confidence region, or 90% central confidence region, or 95% one-sided confidence region, or something. So confidence regions come into final answers, and 68% might have a place there. If you're talking about systematic errors, then you're presumably talking about one uncertainty in a whole lot of different systematic uncertainties, and then there's the statistical uncertainties on top of that. You are going to roll those all together and combine them in quadrature. And the central limit theorem, bless it, says that if you've got non-Gaussian errors, then variances still add in quadrature. So if you've got lots of different contributions to the systematic error, you can add them in quadrature and get a total contribution to the systematic error, which is also the standard deviation. And actually, the central limit theorem then kicks it again and says if you've got lots of these contributions, then what you're getting out is going to look quite like a Gaussian. So for systematic errors, you're probably better off using RMS spread. If you are using a 68% confidence region, and if you take an ultra-frequentist approach to systematic 68% confidence, which says that you must never, never, never undercover, and over-covering is fine, then you've got to have something which will be true at least 68% of the time. And if it's 69% or 99% of the time, that's fine, provided it's at least 68%. Then in that cases, you have to consider all possible values of the nuisance parameter and take the widest. However, I don't think you're likely to be doing that, and if you are, you know it. And if you are going this 68% central confidence region for a non-Gaussian, then you can no longer add in quadrature. The two are incompatible. So there are cases where you should take the maximum deviation as your error, but you're probably not using them. You should not be afraid of quoting a result which is more than one standard deviation from the true value. Indeed, you should be doing it 68% of the time. Yet people persist in talking about taking the largest deviation because it's conservative. I've asked them, they say, well, it's what we always do. It's what my supervisor told me to do. It's what the analysis group does. It's what the guy that did it last time does. This is not a valid reason for doing anything. We're supposed to be intelligent physicists who know what we're doing and why. People are worried that, suppose one day they do the measurement better and it turns out that the value is a little bit outside the errors we quoted. Well, that's okay. 32% of the time, that should happen. And the other word which people use is they say, well, it's conservative, and think that that's an answer. But when you're talking about statistics, when you're talking about errors, then conservative is another word for wrong. That may or may not extend to other fields, but in estimating errors, it's certainly the case. So please do not defend yourselves by saying it's conservative. Talking of conservatives, anyone remember this guy called Donald Rumsfeld? He did lots of stuff which in those days seemed bad stuff, although it's fairly moderate these days. But he did come up with his absolute gem of a statement. He was talking about weapons of mass destruction being hidden in Iraq or not. And he says, as we know, there are known knowns. There are things we know that we know. There are known unknowns. That is to say, there are things we know we don't know. But there are also unknown unknowns. There are things we don't know. And now, he wasn't a particle physicist, but he certainly got that right. There are things we don't know. I said right at the beginning that Bevington was wrong and ThorEA was right, that a systematic error was not a mistake. But mistakes still happen, and I can't just go all lawyer on you and say, well, systematic errors are not mistakes, so I'm not going to consider them. They happen, and we need to be aware that they will happen, as statistical tools can help us to find them, although they don't always give the solution. And there are two tools for this. One is to repeat the analysis by changes which should in principle make no difference, and then see if they do. For example, you might take the data which was taken last year and the data which was taken this year and see if it gives the same results. Of course, it should, but there are lots of reasons why it might not. In LHCb, which I work on, we have a big magnet which can be powered in either direction, and we switch it round every few weeks or so when we're running, and it's standard to look separately at the magnet up and the magnet down data and see if there's any consistent differences there. You can also change your selection cuts. You perhaps have a cut on the energy. If you reduce that cut, then you let in more background, but you also let in more signal. Your signal goes up, but your background goes up. Your final result should be compatible. If you make it stricter, then you've got a purer sample, but a lower efficiency. Again, the result should come out to be compatible. You can try changing the histogram bin size, changing from a unbinned maximum likelihood to a bin maximum likelihood to a chi-squared, ranges of fit and what have you. Try changing the fit technique, method of moments or maximum likelihood or what have you. So you make all these changes which should not make any difference and see whether they do or not. The second technique is to look for impossibilities, things which cannot be there, and see if they are. For example, the first observation of CP violation in the B mesons by BaBar, also by Bell, the paper says they performed consistency checks, including separation of the decay by decay mode. That's the decay of the B to psi K0. Tagging category, that's what's happening on the other side of events. B tag flavor, the B's versus B bars. So they separated them up, divided them up into different samples, and saw they got compatible results from each. We also fit the samples of non-CP decay modes for sine 2 beta. Sine 2 beta being non-zero is a sign of CP. They looked for evidence for it in cases where it could not be there, and it was not there. Fine. So on that basis, they had a credible results. Right. So you do these checks, you do a check, it passes. Fine. It just gives you a little bit of a difference. If you look at last year's and year before's or what have you data, there's a small difference between them, small enough to be within their statistics. What do? You say, hooray, you tick the box and you move on. You do not say, hey, there's a discrepancy, I will add that to the systematic error. Why? Because it's stupid. It's illogical. You've set out saying there is basically no difference, or there can be no difference. It penalizes diligence. Again, somebody who does hard work and does lots and lots and lots of these checks gets lots and lots and lots of small deviations. They do not have to add those up in quadrature and increase their systematic error. And in this way, by doing this, your errors will get bigger. The LEP results agreed within some ridiculously small number of standard deviations with the standard model at the end of the day. So this is, if it passes the test, that's it. Tick the box and move on. You can't prove your analysis is correct, but the more tests you do and the more tests it passed, the more confident you and your colleagues and your audience will be with the result. What happens if it fails the test? Okay, you have a problem. The first thing to do is check the test. Very often it turns out that it's the test which is at fault, because you have spent several weeks, months devising the analysis and taking great care over it, and you've spent afternoon devising this test and running it. Maybe you've missed something in the test. It's had a lot less work going into it. Okay, you check the test, it's fine. Check the analysis, and perhaps you find the result. Oh God, that minus sign should have been a plus sign. Put it right and enjoy the improvement. Hooray. You check the analysis, you can't find anything. Worry that this might be real. For example, you've got results from the June run and the July run. June and July, both go with J. How can they be different? Well, maybe July was hotter than June. Maybe there's some temperature effects in your apparatus. I didn't think of that, did I? No, right. Think of how you would compensate for this and perhaps introduce, correct for it if you can, introduce an implicit uncertainty if you can't. And if you can't think of a plausible reason for the difference to be real, keep worrying. Ask your colleagues, raise it at your collaboration meetings, look at other experiments and see what they've done, pick other people's brains. As a last resort, you add it to the systematic error, but only as a last resort, only after you have really sweated some blood over it and lost sleep. Here's a toy example, I hope slightly realistic. This represents an energy calibration. This is the data, the value, the output you get from your photomultiplier or whatever it is, and this is the actual energy that went in, and the true values are given by these circles here. I've suppressed error bars because the plot's quite complicated enough already. For some reason, you don't spot this nice quadratic function, and you fit it with a straight line. That's that dashed line there, which is not such a bad fit to those points. Fine. You get a slope, as it happens, of 4.0. Okay, so you use that in your analysis. Then you're doing a check. So you say, well, maybe I could split this in two, and I'll look at values in the below 5 and values above 5. Fine. And if you do that, you get rather different results. You get these dashed lines, dotted lines here. This one has a slope of 2.5, and this one has a slope of 5.6. So you've got a problem. Despite all my words about worrying, for some reason to make it the story held together, you fail to spot that this isn't really a linear calibration. And you say, well, I've got a slope of 4, but I'll give it a plus or minus 1.6, say. And that is terrible. Because, okay, there is also an error on the constant, but I'm not discussing that. It just makes things more complicated. The dashed line is not that bad a fit to these points here. And assigning that an uncertainty of plus or minus 1.5 is grossly too much, and you're overestimating your errors when you're interpolating. On the other hand, if you're going to extrapolate, say out to a D of 20, this is going twice as far on the right-hand plot, then your straight line, even with a plus or minus 1.5 on it, is a very long way away from where the true value is. So for interpolation, it's far too big an error estimate, and for extrapolation, it's far too small an error estimate. Just saying, oh, well, add it to the systematic is not good. I think, to clear up one possible confusion, I've said that when you're evaluating the second type of systematic error, you vary your Monte Carlo parameters and what have you, and you see what happens to the results, and you add all those up and you include them in the systematic error. I've also said that when you're doing checks, you vary lots of parameters, you see what happens to the result, and you don't include that. You mustn't include that in the systematic error. So what's the difference between the two? Well, there are two differences. The first is really, are you expecting to see an effect? And if you've got the jet shape parameter in the Monte Carlo and you're looking at something in the data, then I would expect there to be some sort of effect on the results. And so the question is not, is there an effect? The question is, how big is the effect? Because we know it's there. And the other hand, if I'm changing a cut and the efficiency goes up, but the background goes up and they should compensate for each other, then I'm not expecting to see an effect. The other touchstone to work with is, do we know how much to vary them by? When we've got a Monte Carlo parameter, then that comes with a description of how uncertain it is, and we know how much to vary it by. If we're changing an energy cut, we just, change it by 0.1 or 0.2 or 3 JeV or some sort of round number just to see what will happen. There's no definite reason for choosing any particular number. So that's the second touchstone. And that covers sort of complicated hybrid cases like suppose your energy calibration is uncertain, but it feeds through to the first level trigger, and it's easier to vary the energy of the first level trigger rather than the energy calibration of the calorimeter. Okay, so that is, I think, quite enough. I have talked for almost an hour. I am going to leave you with these 6 commandments. There might have been 10, but 6 are quite enough. Try not to talk about systematic errors, and certainly if you do, know whether you're talking about a systematic effect or a basic mistake. You should know whether what you're doing when you go through this, changing that, and see what happens, whether what you're doing is evaluating an uncertainty which adds to the total contribution, or whether it's just a simple check for a mistake that you hope it passes. If your check passes, do not add that to the systematic error. If your check fails, do not add that to the systematic error unless you've absolutely thought of everything other possible that you can. If you've got uncertainties on uncertainties, do not add them in quadrature. Ignore them unless they're too big to be ignored, in which case you need more Monte Carlo. And finally, and most important of all, know what say what you're doing. Don't just say the systematic error is this. Say we varied this, we varied that, the uncertainty gave it, etc. So say what you've done and be able to justify why you did it, not just because the guy did it last time, or well, my supervisor told me to do it, or well, we asked the statistics guru and he said so and so, or somebody I met down the pub told me to do it. All of which are known. Know what you're doing, be prepared to justify it yourself. So that is your systematics chapter. That is the ideas behind it. I wish you the best of luck writing it. I'm sure you're in for a very exciting time. Thank you.
Thank you, Dr. Barlow. I think this was very helpful. It's really good to see that there can be some concise set of prescriptions to help us, to guide us through this topic. So let's now open the floor for questions.
Hello.
Hi.
I have 3 questions. So first on page 13.
Yep.
Right. So like with N models. So the formula for N models, explain it in more details. Like what is the mean R squared minus?
Oh yeah. Yes, I'm sorry. That's not very helpful, is it? That should be R squared bar minus R bar squared. That's okay. Does that make more sense?
Yeah.
Yes, it's the root mean square difference between the models, spread between the models, including the usual n over n minus 1 correction.
Okay. But why is where does the why is the coefficient n over n minus 1? Like
N over n minus 1.
Yeah.
Oh, that's the usual estimation of a standard deviation when you've got a sample and you don't know the true mean.
Okay.
I think it's called Bessel's correction.
Okay. Okay. And next question is on Slide 20, yes.
Yep.
Sometimes when we do a check, sometimes we do a check because we expect there's no difference, so it's a check. And when we do it, although we expect it to be the same, but in practice, it's very hard to be exactly the same. Like in practice, it's kind of impossible to get exactly the same result.
Very suspicious, yes.
Yeah.
Yeah.
So how different is acceptable? Like, is there a quantitative way to?
It depends on the particular check that's being done. If what you're doing is you've got a data, yep, and you've got a subsample of data, then if you work out the error, you'll get an error on the result from the data, and you'll get an error from the subsample, and the error from the subsample will be bigger,
yes,
because it's a smaller sample, yeah. Then if you take the difference in quadrature between the big error and the little error, the square root of that gives you the error on the difference. And that's, okay, so that's exact if the check you're doing is sample, subsample, look at the different results, it's in difference in quadrature. If what you're doing is something more not so simple, like say a maximum likelihood fit rather than a chi-squared fit, then that is still approximately true. So you can take the larger error, subtract the smaller error in quadrature, and that gives you a benchmark for comparing the difference against. It's not quite fair to compare it with the overall error, although people can do that, because of course, a lot of the overall error comes from the particular data that you've got, and that's common to both samples or both analysis techniques. So difference in quadrature is the best answer you can get to that.
Yeah, so a difference in you use a subset to you use a subset of the data and get an arrow, and you can calculate the value like subtracted by the arrow on the whole data set and take the square root.
Yep.
That's the value. And how do you use the value? Like you come, how do you use the value as a benchmark?
Okay, so suppose you have a result of let me invent a number, yeah, 100 plus or minus 4. Yep. And you do it another way, and we have a result of 102 plus or minus 5.
Okay.
Say, yep. Then I subtract 4 from 5 in quadrature, and I'm using Pythagoras again, so that's 3. And then I say, okay, I had a difference of 2, as it went from 100 to 102, and I would have expected a difference of 3, so it's less than 1 standard deviation, so it's not significant.
I see.
If I had started off with 100 plus or minus 4, and I had gone to let me say it 109 plus or minus 5, yep, then I would have said, oh, that is a difference of 9 with a standard deviation of 3. So that's 3 standard deviations. So that's looking like a problem.
Okay, I see. Okay, thank you. And one last question is on slide 22.
Yep.
Yeah, maybe I'm mixing two concepts here, but sometimes we do the check and it failed the check and I worried, but no result. So I have to I have to take it into account in my final result. Then you say the last resort is to add a term to the systematic error. But I also heard, like previously, you say we should subtract it. So maybe I'm mixing concepts here.
Yes, that was talking about something else.
Okay.
That was yeah, that was talking about a variation in a parameter. And this is talking about a check which should have no change.
Okay. So in this case, in this case, in order to add them, I still add them in quadratic, right?
Yes, you shouldn't add it, but if you do add it in quadratic.
Okay. I see. Thank you. That's all.
We got a hand up.
Hi, can you hear me? This is
Yes.
Kong. Very nice talk. Thank you very much. And on your slides 3, I really like the definitions of systematic error. And I was, before you showed your slides, which is right and which is wrong, I somehow feel like there are cases that mixing the two. For example, if you have a faulty equipment, for example, in our star or any detectors, sometimes there will be faulty channels and things like that.
Yep.
And you know there is a hole, or you know there is a bad channels, and that will be definitely caused by anything and is a faulty equipment. And then when you're doing analysis, for example, you're reconstructing a jet, particles, momentum, event planes, or whatever. And then you will vary some of the things on the right, for example, your efficiency, your acceptances, and then that you will get a systematic uncertainties. So how do I understand this? How do I understand this faulty equipment that we know is faulty?
If it's faulty and you know it's faulty,
yeah.
then that introduces an effect, and you know that you hopefully know how big that effect is, or maybe there's an uncertainty in it. So if you have a detector which stops working, as they do,
Mm-hmm.
And you don't know this, then that is faulty in Bevington's sense. If you have a detector which is not working and you know that, so you include that in your uncertainties and your simulations, then that's a systematic error. No, that's that's then known exactly. If you've got a detector which failed sometime during the run and you don't know when, then that's introducing an uncertainty into the systematic effect, and that is a systematic error. When Bevington is talking about faulty, and it's clear from the rest of what he writes, he is explicitly meaning something which is faulty and you don't realize it's faulty.
Okay, I see. But I mean, this is kind of going in loops, right? I mean, if you don't know it is faulty, then you never know, like, if you exist. And then when you vary something that, for example, your efficiency or whatever, as a systematic check, and then you will definitely assign them as a systematic uncertainties, right? These uncertainties will account for the unknowns, like what you said, the unknown unknowns. Is because you don't know if there's a failure, and then you vary something that actually reflect a differences or a systematic change, and logically, that would you assign that as a systematic uncertainties?
If I knew it was dead, it wouldn't be uncertain. I would just have a dead piece of the apparatus. If it is dead and I don't know it, then that's a mistake, and I pick it up with a check. If it is kind of sick, if its efficiency has fallen, but I don't know how much to, or perhaps it died at some point during the run, then that's an uncertainty on a systematic effect.
Okay, I see. Okay, just
Okay.
very quick question. I mean, any of this definition might be subjective, but in your slides 13 or 12, when you said, very interesting because we encounter this problem all the time, is note 2 that you have errors due to the Monte Carlo statistics, right?
Yep.
And very often in experiments, we also have systematic uncertainties. We have errors due to these data statistics, not just the corrections using Monte Carlos. And very often, there's a very difficult task is to how to distinguish your systematic uncertainties from your statistical uncertainties. Most of the time, people will quote the systematic uncertainties, but it's actually quoting part of the statistical fluctuation as well, because your data precisions is not very well, and then you do have statistical fluctuation in your data, and then when you evaluate your systematic uncertainty, sometimes you quote partially from the statistical fluctuation. So what do you think of this problem in general?
It's an important question. It comes up a lot. I think the answer is that it makes no difference provided you say what you're doing. There was certainly a time at which BaBar and Bell were quoting results on similar channels. Mm-hmm. And yes, there were backgrounds which were calculated, but they were calculated from other channels in the same experiment. And one experiment called them systematic and the other called them statistical. So the results looked very different, but when you added them in quadrature, they were commensurate. So provided you know what you're doing and say what you're doing, it doesn't matter whether you call that particular contribution to the error systematic or statistical.
I see. I mean, that is a perfect way to do it, but sometimes I think people double counted it, right? I mean, they say this is the statistical fluctuations and they quote as statistical errors, but then they independently evaluate some of the systematic effects, and then they assign an independent systematic errors, but which this statistical error and systematic errors are actually correlated in some ways, if it's affected by the statistical fluctuations.
Okay, that is a
I think it's just a practical challenge.
I haven't actually met, but I'm quite prepared to believe people are doing it and they shouldn't.
Okay, good. Thank you. Thank you very much.
Another hand?
Yeah, thanks a lot for the talk. I had a question on the interpolation part. How do we know the degree of the polynomial with which should fit the data? Because if we take a polynomial with a higher degree, it will fit the data exactly. But when we increase the the x-axis, it might not be giving the correct results. Like, how should we determine the degree of the polynomial with which we can fit the data?
You can increase it, and then you can use what's his name, Wilks' theorem. If you increase the order of a polynomial, you will get a better fit to the data, obviously, because you've got more parameters. Yep. And if the increase in chi-squared is of the order of 1, then you haven't done anything. So you start off, if you like, with a straight line, or the best straight line, the best parabola, the best cubic, and the chi-squared will get better and better. But if the chi-squared only gets better by about 1, then you haven't done anything to fit the data better. And also, obviously, you keep track that it's doing sensible things. And, yeah.
Okay, thanks a lot. Yeah.
In this particular case, I had assumed, and I think it's indeed true, that if you take the background in the background regions and all these different curves, then they fit adequately, but not super adequately. Well, there's a question from Dan Lianage about how to find the covariance matrix. Basically, you write down the expectation value of x minus mean x squared, or xi minus mean xi times xj minus mean xj, and multiply it out and put in what you've got in the way of means and standard deviations, and everything that is independent will cancel with something else, and it just drops out. If you look at the paper I refer to, there are various examples of that.
So maybe then let's take questions from the raised hands. Yuhu?
Yes, thank you. Can you hear me?
Yes.
Yeah, very nice talk. Very impressive. Thank you. So I have a question, follow Kung's question. He mentioned about if people estimate the systematic uncertainty and also estimate the statistic uncertainty, they just simply add them, and that will overestimate the uncertainty. So I know there's a method that we first compare the systematic, the mean value different between the two different model, and then decide if that one should be counted into the systematic uncertainty. But I'm worried about, well, in this way, we underestimate the systematic uncertainty.
Why might you underestimate it?
Well, you first compare between the different, whether this systematic should be count in, but in this way, right? You didn't take the statistic uncertainty for that value into account. For example, you have model 1 and model 2, right? Okay. You first compare the difference between the for the mean value for model 1 and model 2, but in this case you don't have any take any account of the uncertainty for model 2. You only compare the mean value. So will this way, I think you got my point. Well, this way we underestimate it.
If anything, you're overestimating, I think. Mm-hmm. So you use it using model 1 and you get, say, 10 plus or minus 1, yeah? Mm-hmm. And you do it using model 2 and you get, say, 11 plus or minus 1. Mm-hmm. And let's assume that these plus or minus 1s are independent. Mm-hmm. Then the difference between 10 and 11 gives you a difference of 1, mm-hmm. which is the only real number you've got. Mm-hmm. In fact, if you say, well, that's 1 plus or minus 1 plus or minus 1, actually, it is quite likely that this difference of 1 comes from the uncertainties, the plus or minus 1s afterwards. So the 1 is, if anything, going to be an overestimate of the difference. If this model resolutions mm-hmm. are appreciable, then you need more model data. You need to run that model for longer or something.
I see, but okay. But
remember that the overall error includes the error on the particular data sample you happen to have, which is the same for both. So you have to find some way of pulling that out.
But if different model, we have different statistics, then the statistic error for different model will be very different, for example. And for one cases, you have a very poor statistics, so have an extremely large uncertainty. So when you try to find the different, right, it's always below smaller than this individual, the model 2, for example, right? Then you will never have any systematic uncertainty, but certainly need to have them.
Okay, so model 1 gives you 10, yeah, plus or minus 3, which is due to the data, plus or minus 2, which is due to the Monte Carlo statistics on model 1, yeah? And model 2 gives you, no, let's make it bigger, let's say 15, yeah? Plus or minus 3, it's the same data, yeah? Plus or minus, again, 2. Now, the plus or minus 3 is the same, so you can't use that in the comparison because it's due to the randomness of the data and it's the same data. So you have 10 plus or minus 2 against 15 plus or minus 2, and that's a difference of that's a systematic difference of 5. Now, so I would quote a result on that of maybe 10 or maybe 12 and a half, plus or minus 3 statistical, plus or minus 5 systematic. I'm ignoring the plus or minus 2s that came due to the systematic, to the Monte Carlo statistics. If those plus or minus 2s were large compared to 3 or 5, then I would have a good case for saying, I can't do this, I need more statistics, give me some more computing cycles.
I see. Okay. I think I got your point. Thank you. Thank you very much.
Okay, so the question by Aditya, I think I should narrate it for the video recording. So what they write is, if we remove the data from the end part of the x-axis and fit the central data points and find the lowest order polynomial which fits the central data as well, as generalizes, well, when we fit it to the end part, which we had initially removed, can it give us some confidence on the degree of the polynomial to be used? And they provide example. If we take data from with x from -5 to 5, can we fit the data between -4 to 4, and then check if it also explains the data at -5 to 4 and I guess -4 to 5. And I guess this overall ties into maybe similar to what we do when we have training set and the test set in machine learning. So that's the question.
It's not quite the same as training and test. A thing about polynomials, yeah, is that they are great for interpolation and rubbish for extrapolation. So if you can get a polynomial to fit between -4 and 4, I would be very surprised if it did anything sensible between 4 and 5 or -4 and -5. So if you're just using a polynomial, I don't think it's a fair test to try and extrapolate with it and see if it does any good. You can try fitting some data set points, yeah? And you fit a cubic or a quartic or something, and it gives you a nice smooth curve in the bit you've generated the points. But as soon as it gets outside that, it will do that or that. So yeah,
So I guess your answer has to do with just the properties of polynomials.
I would say, yeah, okay, it's not a very helpful answer, is to say that's the wrong question. But the first, okay, so first I would say don't ask a polynomial, don't extrapolate a polynomial. It really isn't a fair test for it. You could, okay, apart from that, yes, you could also try fitting the data in the background bit and the data in the signal bit. But to do that, you have to have a recipe for what the shape of the signal is. Now, maybe you do, maybe you don't. The particular case I was considering, I didn't. I just was counting a number in there. If you do know or think you know what shape the signal can be, and there is probably more reason to think you know what shape the signal should be than what shape the background should be, then you can use that. And that makes it a more complicated problem. But again, you say, if I fit this with a crystal ball plus a cubic, I get chi-squared of 97, whatever degrees of freedom. If I fit it with crystal ball plus a quartic, I get 83. That's a big improvement. If I fit it with crystal ball plus a quintic, I get only 82. So that's not worth having.
So the next question is by Somaduta.
Hi, can you hear me?
Yes.
Hey, hi. This question might be a little bit specific. This is regarding fitting a distribution with functions. So suppose you have a distribution and you are fitting it. You are trying to describe the data by fitting it with, let's say, two different functions A and B. And let's say, obviously, these functions might describe some specific region of the distribution very well, and the other part of the distribution it may not describe very well, and vice versa for the other function B, let's say. So how do you actually, obviously these two functions might have also different physics goals, or what kind of physics they want to describe from the distribution. How do you actually decide which function has more power to describe your distribution? Is it just by like taking calculating the power by taking a null hypothesis, assuming that it doesn't describe the distribution at first and then you describe the power? Or is there any other way to determine which function has more power to describe your distribution?
The chi-squared is the obvious tool to use for this.
Yeah.
And you can adjust that if your functions have different numbers of free parameters. So whichever gives you the better chi-squared, and you can back this up with things like the run test. And if it's multidimensional, you can use the energy test and various things like that. So chi-squared and its friend, it's a goodness of fit problem, and there's a lot of material on that. I would say you want to distinguish carefully between functions like the Gaussian, like the crystal ball, where from like phase space, where from physics or from prior knowledge or something, you have a real belief that this function is describing the data, and functions like a quartic, a quintic, cubic splines, where you're just saying, well, I guess I can draw some sort of curve through that and parameterize that in a simple way. So the difference between functions which are driven by some belief they're actually telling the truth, and functions which are just convenience.
Okay, but how about this? So these two, I understand your point, but suppose you're trying to, so suppose there is some standard way in which people try to describe the data by fitting some standard function, and it's like the standard which everybody does. And suppose we are trying to look for some new physics from the same distribution by fitting a different function, and you have obviously some background to motivate you to believe that it actually can get you some new physics. So how do you actually, so in this case, especially, how do you determine if your new test of the fit is good enough in comparison to the standard things that people do? Apart from, apart from chi-square.
If it can do it using fewer free parameters, if you've got some belief, say that there is a bump at some value, then if you can accommodate your distribution by a simple polynomial and that bump, as opposed to a very complicated polynomial, then you've got a case for saying you've got something. So you've got to have fewer free parameters to get the same chi-squared, or a better chi-squared with the same number of parameters, or equivalent to chi-squared.
Right. Okay, I got your point. Thank you.
The question from the chat says by Dan Lineage. Thank you for an answer. I have a follow-up question. How would you find and include systematic correlated uncertainties in this covariance matrix? Would the method you explained will also capture the systematic correlated uncertainties between different observables?
Yes, it does. It is basically, it's nothing but the good old combination of errors formula. Sigma f squared equals df by dx squared, sigma x squared plus df by dy squared, sigma y squared, plus rho xy, sigma x, sigma y, df dx, df dy, generalized to as many variables as you have. So it's the standard combination of errors, but with the differentials and written in a matrix form. And then provided everything is Gaussian and small, you're laughing.
That was a thanks. And for the last question by Debashish.
Hi, can you hear me?
Yes.
Yes.
Okay, so I just looking at the slide number 12. So where you saw the asymmetric error, you have a plus 0.5 minus 0.3. You put that as average of them, plus minus 0.4. So how do you make a judgment there if the asymmetric error is, the asymmetry is large between plus and minus errors? Or you don't do any averaging?
If the numbers, the 3 and the 5, are similar, and if they're small, then I would approximate them as being symmetric. If I possibly could, if I thought I could get away with it. I do not have a definite hard and fast rule for that, I'm afraid. But I would honestly say you will save yourself grief if you can steel yourself to make them symmetric.
Okay, so if any cases like a parameter, you know, the quantity is fixed in its lower value or upper value. For example, if you're talking about efficiency, then efficiency should not go beyond 1. So if like So when doing this averaging, like you might cross that limit in upper bound or lower bound, right?
Yes, that would certainly ring an alarm bell. And I would try and think of reparameterizing the algebra in a way which didn't go there.
Yeah, so before doing
Luckily,
this
none of
averaging,
us
you
have
might-
efficiencies
yeah.
which are that close to 1.
Yeah, okay. So you might need some information about the parameter before taking a approximation. Yeah, right. Yeah, okay. Thank you.
Thank you again, Dr. Barlow, for teaching us all about the uncertainties. This was certainly a very helpful talk, hopefully with very lasting consequences. And
Thank you very much for asking me. And I think you have a really exciting experiment, and I wish you the best of luck with it.